Right, so in this module, we will start talking about influenza virus. Influenza viruses are coming from a family called the orthomyxovirus family. They're enveloped virus, which means that when they exit the cell, they take with them a membrane bilayer, which is taken from the host cell. On this membrane, or also known as the viral envelope, we have two proteins expressed that come from the virus. One is neuraminidase, which is an enzyme which cleaves sialic acid ends in glycoproteins and glycolipids found on the surface of epithelial cells, and so basically facilitates the permeation of the virus through the mucus secreted by epithelial cells in the upper respiratory tract. Hemagglutinin is a protein that binds sialic acid, and so sialic acid is expressed again on glycoproteins on the surface of these epithelial cells, and so facilitates the attachment of the virus to the host cell. And it's actually the equilibrium between neuraminidase activity and hemagglutinin that makes the virus infectious. So let's look a little bit more in detail what happens during the life cycle of the flu virus. So first we have absorption. So again, this is when the hemagglutinin recognizes its target. Once several hemagglutinin molecules are engaged with glycoproteins expressed on the surface of the cell membrane, then we have endocytosis. So we form an endosome that is taken up inside the cell. And the endosome, so this process is called endocytosis. The endosome is characterized by very low pH, and that causes hemagglutinin to have a major rearrangement in structure, which we'll see in a second, and that in turn causes the fusion between the RNA nucleocapsid and the cytoplasm of the host cell. And so in other words, we have what we call uncoating of the virus. Once the virus is uncoated, then it basically takes out single-stranded RNA with negative sign, which is then translated to positive sign single-stranded RNA, which is basically mRNA, which is then taken to the cytoplasm and translated into viral proteins. Once again, then the viral proteins reassemble to form a capsid, and which contains all the components of the influenza virus. And then note that viral proteins are also secreted into the cell membrane. And then we have budding of the virus, so the new viral particle gets secreted basically by the host cell in active part. So we can classify influenza viruses in three main types: A, B, and C. A infects a variety of organisms, including us, birds, pigs, horses, and etc. The birds have the natural hosts, and we have several subtypes that depend on the sequence of hemagglutinin and neuraminidase. And so influenza type A is what we typically talk about every winter when we talk about influenza epidemics. Then we have type B, which is less common than A and has symptoms that are not so bad. And also the mutation rate is much less than A. Influenza type C is really not a concern because for the most part, it basically causes only mild illness in people. So what causes resistance, both to the vaccination efforts and to some of the antiviral agents we will form? We have antigenic drift, which is basically mutations to HANA that occur over time, and so those are very gradual. And that causes antibodies to not recognize the new virus anymore. So we provide only partial immunity, and that's why we get the flu every year. And that's a constant change, basically. And then we have what we call the antigenic shift, which is an abrupt change in the sequence of HA or RNA, and that results in the sudden emergence of a new subtype, and that's very dangerous because the population is naive, doesn't have any protection to this new virus, and so we have epidemics or pandemics. So influenza A has both types of changes, whereas B only changes by antigenic drift, and so we have time to get used to it. Now let's look a little bit at the site of actions of anti-influenza agents. So we have several processes. So again, we remember we talked about absorption, where we have interaction of hemagglutinin with a receptor that has sialic acid. We then have endocytosis, and then during endocytosis with low pH, hemagglutinin rearranges and uncoats the virus that then gets released into the cytoplasm. And so we have adamantanine derivatives that basically work to prevent this uncoating stage. And then we have, again, going from negative sign to positive sign RNA, messenger RNA that forms, and then we have, again, repackaging and budding of the cell. So we have two classes of compounds that act either, basically preventing the synthesis of positive stranded RNA from single-stranded one at two levels, either by targeting the GTP supplier, by targeting RNA polymerase. And then we have most important and most common neuraminidase inhibitors that prevent the release of the mature virus into the environment. And so, as we already said, basically the challenge for influenza virus is the balance between hemagglutinin, which binds to sialic acid, and neuroagglutinin, which neuraminidase rather, then basically cuts off the sialic acid attached to the glycoproteins. And so that's a problem for the virus, because when the mature virus is ready to be released, then neuraminidase needs to cut the bond between the receptor and the virus itself to have release. And that's the target where we can have. So let's look at the role of hemagglutinin in viral entry. So we have hemagglutinin expressed on the membrane of the virus, and it's a trimeric protein, and again it's extended out from the virus. In its folded form, it hides what we call a fusion peptide, which is an unfolded peptide that is in charge of fusing the viral cell membrane with the host membrane, or in this case with the endosomal membrane. So when we have a low pH, we have a rearrangement of hemagglutinin, which releases the inside part of the protein and exposes the fusion peptides. And so we have at this point the fusion peptides that is extended out to the target membrane. The other part of the protein is still attached to the viral membrane, and this proximity causes the fusion. So hemagglutinin is crucial for viral entry. So the important protein here is a viral protein called M2 that allows for pH equilibration between the endosome and the virus. And so it acts really as an ionic channel and permits the rearrangement of hemagglutinin. So these drugs were discovered by random synthesis, and so at higher concentration, these compounds dock inside M2, this viral channel, and basically prevents its action as an ionic channel, and so they prevent basically the uncoating of hemagglutinin.